Stable Diffusion XL. It came out last week, and it is a really good model. So you've probably seen Stable Diffusion before. It's an awesome open source diffusion model, and all the images you've seen online, they may have been created by Stable Diffusion. Stable Diffusion is just it's open sourced, it's awesome, it's nice, and this is also open source. So it's great to see these diffusion models be open source so that the community can kind of develop them, make them even better. And Stable Diffusion XL is the next improvement on Stable Diffusion, and it's the reason it's XL as opposed to I think 4.0 now. I think Stable Diffusion was on 3.0 is because they have a lot of architectural changes in the model itself, as opposed to just changing the data or trying to improve data quality. So Stable Diffusion XL, let's get into it. So first off, uh, what is Stable Diffusion? Now I have created a video on Stable Diffusion. So if you're interested in like more detail, I would check that out. But I do real quick want to go through like basic Stable Diffusion at a high level. So if you already know that, go ahead and skip this. But yeah, so let's get started with a picture of a cat. So we have our cat looking like this. There we go. Amazing cat. So this is your input image. Now what you do is you add a little bit of noise. So we'll add a little bit of noise, and I'm going to copy this. There we go. And I'll paste it again right here, and one more time. There. All right. So you add a little bit of noise, which I'll represent with red. So a little bit of noise, and then so this will be, say, time step t is equal to 0, t is equal to 1, and then you add a little bit more noise to this image, so t is equal to 2. So, whoops, don't want that. A little bit more noisy. And this noise is sampled from a Gaussian distribution. Z or epsilon, whatever you want to call it, is sampled from a Gaussian distribution with mean 0 and variance 1. And you keep on adding noise over and over again until you get time t is equal to big T, which is usually 1,000. Usually in practice, you'll see this as 1,000 time steps. And in this case, you won't have the cat at all. It'll just be this really noisy image, and this image is going to be sampled from a Gaussian distribution. So this at time step big T is a Gaussian distribution. It's sampled from a Gaussian, and your original image is the image without any noise in it. Now this process is easy. Going forward is easy. You can have a function to do this, and specifically our function will be x sub t. So our image x at time t is equal to alpha t times x sub 0 plus the square root of alpha t, or 1 minus alpha t times, I said z. So what this is saying is your image at any time step within this diffusing process is your original image plus some noise. And this is an interpolation between the two. So whenever alpha t, or alpha 0 is equal to 1, and alpha t is equal to 0. So at time step 0, you have complete full image, no noise, and at time step big T, you have full noise, no image. And you can go anywhere in this process because of the nice Gaussian properties, and you can go there in one step. So what you do is you train a model to remove the noise. So specifically, I will train a model to, first we'll start with the general idea. So I will train a model to say, given this image, I want it to go back. We'll start here. Given this image, I want it to remove the noise in this image to get to the previous time step. So specifically, I just want it to remove the noise to get to one time step less. And this model, say p sub theta, will take in this image, and specifically, what you could do is you could have it predict this image. However, neural networks work better with residuals, so instead I will just have it predict the noise in this image. The noise in this image that is not in this image. And that's how the diffusing process works. And I'll have this same model, p sub theta, that predicts it at any time step. And p sub theta is a model given x sub t, and time step t, it'll predict the noise. So that'll be equal to z. So it'll predict the noise. And it actually won't just predict the noise in this image. You can train it even better than that. So you train it to predict all the noise in the image so that it steps all the way back to t0. And this way you can skip steps during inference time. But the original diffusion idea is to just go back one step. And basically all you're doing is you're training a model to reverse this process by predicting the noise. Now, this model, what is it? It's a U-Net. And if you've seen a U-Net before, it will take your image in here, your image of cat. Okay, whatever. There's your image of a cat. And it will feed it through some convolution layers, and then it'll downsample it, feed it through some more convolution layers, downsample, some more convolution layers, and then it'll upsample, some more convolution layers, upsample, some more, and then the output prediction will be your noise. So that'll be here. Whatever was the noise in this image. So, but you also have these skip connections here. And U-Nets are very good at this type of task. And you use a U-Net for stable diffusion because it's really good at this type of task. And all it does is it takes in the original image and it predicts the noise. Now, the downside to doing this is it's very expensive. Say I have this 1024 image and I put it through this model. Well, it has to figure out, first off, there's two big issues. First issue is it has to find all features in the image. So it has to manually extract the features while it's doing this U-Net process to figure out what this noise is. And that's kind of difficult. Like, it can do it. It can definitely do it. But it would be better if we can have a feature extractor do this for us. And second off, it's expensive. If you have a 1024 by 1024 image, or maybe you want to do 2048 by 2048, all these convolutions are going to have to convolve over that massive image. So it's very expensive. Now, the big improvement stable diffusion had was it said, well, what if we use a latent space instead? So we do diffusion in a latent space. So what they do is they train an autoencoder. So you have your cat, and so you'll have this trained autoencoder. Let's just say for now, maybe you train it on ImageNet, but you're probably going to want to train it on more. So you have your autoencoder, and this autoencoder will take, this will be your encoder. It'll take this, it'll produce some latent cell, and the latent space is significantly smaller than your image space. But it's not only smaller, but the features are it's very dense. This maybe your image is very sparse. The information is all over the place. However, in the latent space, your information is very dense. It's very dense with information, a lot easier to work with. And then your decoder will produce the image again. So you have your image. There you go. There's your image. And you train an autoencoder to do this. You train an autoencoder just generally on a bunch of images. And then what you do is you train your diffusion model in the latent space. So let me remove this. Now, you can't visualize what the latent space looks like. However, I mean, we can kind of. So this would be time step is equal to 0. This is your direct image, or your direct latents, which I'll call L sub 0. So these are your latents directly from your image. So you diffuse this, and you get a slightly noisy latent, slightly noisy latent. So this would, I'll show that in red, but it doesn't really mean anything. And then you do this again over and over again until you get to time step So this would be t is equal to 1, time step t is equal to big T. And these will be your latents S sub t, and this will be complete Gaussian noise. So this is x sub 0, or L sub 0, and this is L sub t, sampled from a Gaussian distribution, 0, 1. And then you train a model to just reverse this. So you train a model p theta to reverse this process where, given a latent at time t, not the image, given a latent at time t, it reverses the process. So this is just, it's slightly different. Instead of working in the pixel space, you're working in the latent space. And to sample, you would take your, you would sample from a Gaussian distribution. You would feed this through your model. So p theta, it would, this would be time t is equal to t. It would produce an image at time t is equal to big T minus 1. And then you feed this through your model again, and you do this over and over again until you get a, sorry, not image, a latent at time t is equal to 0. And then you throw this through your decoder, and this will hopefully give you a good looking image. And this tends to not only work better, but work a lot faster. So this is what Stable Diffusion does. And if you're more interested in how that's trained, like I said, I made a video on that. Go check that out if you're more interested. But yeah, that's the original Stable Diffusion. Now, how do they make it even better, and how do they get these awesome looking pictures here? So let's just go through it. Let me erase this. Oops. Yeah, let me erase this for now. I'll add that back later. Yeah, so first off, you can see they have 2 units. Let me just erase all this. Yeah, so you have 2 units. You have this first unit here. That's your base. So these are your latents here. That would be L sub 0. And, well, no. This would be, these are your latents at time t. So whatever that may be, your noisy latents at time t, somewhere in the middle of the process. And then this is your unit. Your unit then predicts, say, u sub t. Maybe u sub t is some unrefined latent. I'll just define that as u sub t. And then you have a second unit that refines the latent. So maybe this is r sub t. And then you throw that through your decoder. So you don't just take the output of the unit and throw that through the decoder. Rather, you take the output of your unit, throw that through a second unit, and then throw that through your decoder. And then you get your output image in the pixel space. Now we'll add a little bit onto this this image, but yeah, for now that's kind of what they show. So it's not just a unit. You have 2 units to do this, and the refiner is optional, but it does make the images look a lot better, and we'll get into that. So first off, let's just see what are the comparisons. So oh, I guess there's. Is it only 2? I don't remember. But yeah, you can see that there are some comparisons with that they have here. So the number of unit parameters, you can see that Stable Diffusion XL has a lot more parameters than 2.0 and 1.0. Let me erase all of this stuff. Yeah. So the number of unit parameters is a lot more. So that just means that the number of features that they extract is going to be a lot more. In their convolutions, the transformer blocks. So one important note that they make is that they only use transformer blocks in the smaller, so further down in the unit. So you can see in the first layer of the unit, like the topmost layer, they have no transformer, or they have no transformer blocks. And in the second, they add a little bit more. And in the lowest in the lowest unit layer, they add 10. And they say that, they say it here, we follow this trend and follow to shift the transformer computation to the lower features of the unit. In particular, and in contrast to the original Stable Diffusion architecture, we use a heterogeneous distribution of transformer blocks within the unit. And for efficiency reasons, we omit the transformer blocks in the highest feature level, use 2 and 10 blocks for the lower levels, and remove the lowest level in the unit altogether. So they do this for efficiency reasons, but also because it tends to work better, shown in this paper. So that's a big improvement, but they also remove a whole layer. So they only use 3 layers instead of 4 layers, which is kind of interesting. Now the channel multiples, it's about the same. They just remove the last layer. The text encoder, so this is important. They add another text encoder. You can see that they use clip VITL and open clip VIT8. So for stable diffusion 1, they use that one. They use the clip one, and then stable diffusion 2, they use open clip. And they basically combine the two here. And the way they do that is instead of just having one embedding output, they actually concatenate the outputs. So specifically, we use both of them, and they concatenate the text encoded outputs along the channel axis. They just concatenate them, and as you can see here, they send it through both the base model and the refiner model. So your text prompt is now, they use both of these. Maybe it extracts more features that the model can use, different features as well, feature mix. So that's the first change. So all of these changes are the first change, and you can see the context dimension 2048 as opposed to 1024. So that's where these parameters come from, and pooled text embedding. Yeah, so they add some pooled text embedding, and they use the open clip model again. So now on to the some of the biggest change they made was so they added an extra unit, which we'll get into later. They kind of changed the architecture a little bit, and then they added this big, they added a ton of conditioning to the model. And first, let's just start with the micro conditioning on model image size. So one of the biggest issues with training a model is you have your database, and the database has all sorts of image sizes. Maybe you have one that is 1024 by 20. Maybe you have one that is 512 by 70 by 712. You have this mix of image sizes. Now, some of these image sizes are going to be small. Maybe you have one that is, say, of size 200 by 128. So you have this small image. Now, they show here that if you look at the heights versus the widths of the images, there's quite a lot of images that are smaller than the minimum size. And you need a minimum size because the unit, it subsamples the image, and you can only go so small until you basically get no features, or you get a image that is too small and it can't be sampled anymore. So you have a minimum size for your unit. And they mentioned that there's 2 ways of dealing with this. You can either pad it, or you can discard all samples. But discarding all samples removes 39% of the data, and specifically it's under 256. So 256 is the minimum size, and if they discard the data, then they're losing a lot of data. So you can either discard it or you can pad it. And padding it, they say, the second method, on the other hand, usually introduces. Oh no, sorry. You can upscale it, not pad it. So upscaling artifacts, which may leak into the final model and produce blurry samples. So you have these issues. You can do one, which will lead to a lot less data, or another, which will lead to bad outputs. Now, what they say is, in particular, we provide the original. So they provide. They take the original image, and they have this context. This context comes from. So this context is a concatenation of the height and the width of the original image size. So if we had our 200 by 128 image, then H original would be, say, 200, and then W original would be 128. And the way they concatenate these is by using Fourier feature encodings, and the embeddings are concatenating into a single vector. And then added to the time step embedding. So these Fourier features are just features from, like if you've seen the attention is all you need, it's basically the positional encodings that you have. And it's very similar to the time embeddings in the diffusion model. Basically, you just need a unique way to represent all pairings of these, and you can do so with Fourier features. And you can say, so instead of positional encodings, you would have a time step. Time step is equal to, say, 0, then 1, 2, so on, where your time step is not your time step, it's actually the height of the image or the width of the image. And use Fourier features to encode these, so that's just Fourier features like positional encodings from attention is all you need. The basic attention is all you need encodings, and you just concatenate these together. So maybe your Fourier features gives you a vector of shape 128, and this will encode your H original, and then you concatenate this with W orig. Now, let's add this to the model up here. So they say that you have this, add this here. So you have your time embeddings here, and let's assume that, your time embeddings here, but you add this to your split. This would be H orig, and this would be W orig. So you add this to your Fourier, so you have Fourier features for your time, and you have Fourier features for your original height and width of the image. And these features get sent into the UNet model. And all you do is instead of just taking the time embedding, you take the time embedding and add that to the height width embedding, the height width of the original image, and that goes in the same embedding, and it just works. So it's a joint embedding. And when they do that, you can see that they can basically say what size of the image they want. So they can say that the apparent resolution of the image that they are sampling is 64 by 64. So they're basically, after inference, after training with this context, then you can sample. And you can sample with whatever context, height, width you want. And you can see that as you increase, just C. They keep everything else static, even the seed. And you can see that it definitely learns this context embedding, meaning that it uses these features. So it uses the original resolution features that are sent into the model, and you can see that it clearly has better resolution at 512 as opposed to 64 by 64. And these are the same images. These images are all 512 by 512. The only thing that's changing is the apparent context. Now, one question you may have is, so we still have this problem of like stacking these images together so that we can train it well. And where is it? It's down here. So no, it's not. So the way they do this is they still they go with the second part. They go with this. The second method, on the other hand, is to introduces upscaling artifacts. So they upscale the image, and they feed in the height and width as the context embedding, and that allows them to train efficiently while also specifying the resolution of the image desired. And let's just say I keep it at 512 by 512, or 1024 by 1024, no matter what image I generate, then it'll always look good. And you may be thinking, why is this better than just throwing away the data? Well, it still learns from the low resolution images. It still learns features from there, but you don't get the artifacts from training on the low resolution images from upscaling. So it's the best of both worlds. You get a bunch of training data, and it still learns those features, but you also don't get artifacts from that training data. Now, that's the first thing they do. The second conditioning they do is they condition on another thing. So conditioning the model on cropping parameters. So there's this problem in Stable Diffusion 1 and 2. The original Stable Diffusion is, you can see it crops it. And the reason is because of the random crop. Is because of the random crop transformation or augmentation. So PyTorch requires tensors of the same size. So there's two things you could do: is resize an image such that the shortest size matches the desired target size, followed by randomly cropping the image along the longer axis. So you basically do a random crop. So you basically resize the image so that they're all the same in this batch of images, and that way you can send them through as a batch of images. You can't have jagged tensors yet. Maybe one day. So you have these jagged tensors, or you have these images here, and maybe one looks like this, maybe one looks like this, and let's say we crop them all to that, so that they can be stacked. Then we stack them, and then we send them through a random crop. And whenever we send them through a random crop, that's what gives these artifacts here, where part of the output image is cropped because the model learned, well, that's a good image. Since it's in my training data, why don't I produce an image that's also cropped? And it doesn't know that cropped images are bad. It doesn't know what a cropped image. It doesn't learn that because there's nothing telling it that cropped images are bad. Or there's nothing telling it that it even is a cropped image. But they say, to fix this problem, we propose another simple yet effective conditioning method. During data loading, we uniformly sample crop coordinates, images which specify so it basically specifies the amount of image you crop from the left and the amount of image you crop from the top. So if we were to say crop here, oh man, that is not a good color scheme for me. So if we say crop maybe right here, then we would have these amount of pixels would be C left, and these pixels here would be C top, something like that. Actually, maybe it's more like this, like that. So you have this C left and C top, and you could probably guess what we're going to do is use Fourier features to encode these and add them to the time embeddings. Because let the model figure it out. Let the model figure out how to deal with it. So they say they feed them into the model as conditioning parameters via Fourier feature embeddings, similar to the size conditioning described above. So they do the exact same thing as the method up here, where you take the Fourier features of whatever conditioning you want to do. In this case, it was the relative size, or the size of the original image, and in this case, it's the amount of crop you do. So it's C left and C top. Now you just add that to the time embedding. So let's go back to our original image, and we add this. So we have another embedding that we add to the time embedding, and this is C top and C left. And we just add that, and we train the model on that. So what does that give us? Well, that gives us good-looking images, see Stable Diffusion XL, which are not cropped. You can see it's not cropped. They look good, these images. And the way you can sample good images like this is by specifying you don't want any crop. So they say that here, given that our experience large data set, or given that in our experience large data sets are on average object centric, we set C top and C left equal to 0 during inference, and thereby obtain object centered samples from training models. So you just say, I don't want any cropping in my images, or basically say that there is no cropping in my generated image, and that it generates you an image without any cropping in it. So you're kind of tricking the model by telling it during training that there is an augmentation happening. You're kind of telling it that there is an augmentation happening, and then you basically at the end of training say, I don't want any augmentation, and it gives you a good looking image. Now, if you could probably guess what the third thing is they add more conditioning. And guess where this is going to go? In the time embedding. So multi-aspect training. Motivated by this, we fine-tune our model to handle multiple aspect ratios simultaneously. We follow a common practice and partition the data into buckets of different aspect ratios where we keep the pixel count as close to 1024 pixels as possible, varying the height and width accordingly. So they also want to train at multiple aspect ratios. So you don't just want to train at 1024 all the time. You don't just want to train at 512 all the time. So instead, you're going to train at multiple different scales. So you're not going to keep that scale constant. You're just going to train at multiple different scales. Now, that's the cropping. Yeah, I guess we'll look at that later. So what they do is they also condition on this. So additionally, the model receives the bucket size as a conditioning represented as a tuple of integers, which they send through Fourier features, which they get Fourier features from in an analog to the size and cropping conditioning described above. So they also say, I want to send in the relative height and width, and this will help it out. If you just add the conditioning, maybe it'll help out. Maybe it'll help it out a little bit. So just more conditioning they add. And they say, in practice, we apply multi-aspect training as a fine-tuning stage after pre-training the model at a fixed aspect ratio and resolution to combine it with the conditioning techniques introduced in the section via concatenation along the channel index. So yeah, that's literally all they're doing. They're just adding more Fourier features. So that's all they're doing. Yeah, and that's, if you just condition the model on this, then you can say, I'm gonna give you this image, and the bucket size is say 1024, and the image will probably look better because it's going to try to generate a 1024 by 1024 image, which is usually a good looking image. So let's go up here, and we can add this here. So they also have H target. So this is your target height, and W target. And all these embeddings are joined together and sent through the units to condition them. And that's pretty much, or that's one of the biggest changes they make. They just condition it on a bunch of information, and then you can change this information to give you a better looking output image. And that's they do this with a lot of different stuff, not just time, but a lot of different things. And we can see right here that the crop also helps. So if you do crop 0, 0, if you define the crop, so you do 0 to 56, then that'll be a crop from the left. So you can see that the left is kind of cut off right here. And if you do this crop, then it'll be cropped from the top. And if you do this crop, then it'll be cropped from both the top and the left. But if you do 0, 0, then it's centered. So it's very interesting, and same here. I don't think they have an example of the multi-aspect training. But yeah, they also have an algorithm here for combining the size and crop conditioning. So yeah, that's one of the biggest things they add. It's literally just conditioning the model and then sampling by specifying the condition you desire. Now, you may be interested in how exactly they do this conditioning. So the way they do this conditioning is in the ResNet blocks. So whenever you have a ResNet block, you have your image X, and in their ResNet blocks, they have a norm. So the norm in this case is equal to a group norm with 32 groups. And then you send this through a non-linearity, like that. So non-L, that's what I'll call it. The non-linearity in this case is swish, which is x times sigmoid of x. and then you send this through a convolution, and then you add your time embeddings here. So right after the first convolution, you add your t embedding. And your t embedding, remember, is not only your t embedding, but it's all this stuff. It's all of your conditional information, not just t embed. And then you have another convolution. And the output of this convolution is added to the input as your residual connection. So between convolutions, you add your time information, and that's how they did it, at least in the original Stable Diffusion. I didn't look through I don't know if the Stable Diffusion XL ResNet was available, but this is generally, in general, how you would do this. You would add it. I've also seen it where you scale by a different t-embed. Maybe usually you have like an affine layer here, and you send it through the affine layer, and maybe you also scale it. So you don't just shift the distribution, you also change the variance of it as well. But anyways, this is kind of how you add it in case you were a little interested in that. Now, moving on from the loads of conditional information, they also improve the autoencoder. So they say to this end, we train the same autoencoder architecture. However, they use a larger batch size of 256 versus 9, which is a massive change. And they track the weights using an exponential moving average, so that makes the network like kind of stay similar as it's training. Now you can see that it actually does a lot better than Stable Diffusion 1, and a little better than Stable Diffusion 2. So a minor improvement that they make, and I guess just changing the batch size and adding an EMA helps with that. Now, finally, we get onto the refinement stage. So empirically, they find that the resulting model sometimes yields samples of low local quality. To improve the quality, they train a second LDM, latent diffusion model, in the same latent space, which is specialized on high-quality resolution data and employ a noising denoising process as introduced in SDE edit on samples from the base model. So I just made a video on SDE edit. If you're interested in more about it, it's actually a really cool paper. But real quick, if we go back, actually I'll draw it over here. So let's say we have an image, or latent 0. This would be outputted from our original unit. And let's say we noise it, so maybe this is 100 steps. This is another 100 steps. This would be L100, L200, and maybe L300. So I'm just going to skip by 100 steps, and so on until you get to your L1000. So these would be your latents in your second model. So we're looking, or I'll keep it consistent and call this U. This will be U0, U100, U200, U300, and U1000. So we're looking at this part here, specifically the output of the unit. Now you train a model to take noise and produce high resolution images, or high quality images, and what you do is you take the output latents from here, and you don't noise it all the way. You add a little bit of noise. So you take these, and so you take your original inputs, and you only noise it a little bit. So they specifically only noise it to 200. So we don't need this. We don't need these. So you noise it to only step 200 out of 1,000, and then you re-unnoise it. And what this does is it will, it'll basically take the noise, and as it removes the noise from the latents in this case, it will change the image slightly. The more noise you add, the more it changes the image. That's kind of what they talked in the SDE edit paper. But the more noise you add, the more it diverges from the original image, original latents, but the better it looks. But if you just add, but since we already have latents that look really good, we just want to make them look even better, the image that it'll generate from those latents, then you only noise it a little bit. so that the features in the original latent space stay very similar. However, you can get, since the later part of the diffusion process generates fine-grained details, if you only diffuse to say step 200, then it'll take those latents and it'll kind of change them a little bit so that the fine-grained features within the latents become higher quality. And that's the idea of the refiner. And you use a second unit to do this, and they just do this and train it using the SD edit method, and they say it produces some really interesting results. So like if we look here, for example, here you can see it's like kind of low quality, and then you can see it has a lot more detail in this image here after the edit procedure. And then here's another example. You can see kind of low quality, and it kind of improves the quality using SD edit. I think there's a better example down here, right here. So you can see like the face here, it looks good. The face looks like a face, but if you use SD edit, then it looks a little bit better. Same with the ear. The ear is a little blurry, but using SD edit makes it look more like an ear. And literally all you're doing is you're taking the latents of this image, you're noising them to step 200, and you're unnoising it from step 200. So you can see that most of the features stay the same. The hair is a little bit different, but the background and everything stays the same. It's the fine-grained features that change based on this refinement module. And they say that this helps it, and if you've used Stable Diffusion XL, it does help it. It makes it look better just in general. So that's the refinement module. We note that the step is optional, but improves sample quality for detailed background and human faces. So yeah, it's just an improvement method. So, and that is everything for Stable Diffusion. Those are all the changes they make. And specifically, they use 1,000 steps. So those are all the changes they make. Now, I do think it's interesting to see the failure cases, which they have here. So there's two like really big kind of failure cases. Well, they have multiple, but we'll just read through them. So firstly, the model may encounter challenges with synthesizing intricate structures such as human hands, and it doesn't do a very good job. Like what even is that? And you've probably seen this whenever you've used diffusion. The hands tend to look very strange, and that's like one effect, or that's like one property of diffusion for some reason. It just has a problem with hands, and it's probably due to the data, but they say that this limitation suggests the need for further scaling and training techniques, such as specifically targeting the synthesis of fine-grained details. They state that the reason for this occurring may be that the hands and similar objects appear with very high variance in photographs, and it is hard for the model to extract knowledge of the real 3D shape and physical limitations in that case. So they say that there's a lot of variance with there's a lot of variance with images such as hands, so it may be hard for it to extract, like kind of understand how hands should be generated. So that's one proposition that they make. So we don't know why, otherwise it would be solved, but that's a proposition they make. Secondly, while the model achieves a remarkable level of realism in its generated images, it is important to note that it does not attain perfect photorealism. So yeah, if you look at the images, they're not perfectly photorealistic. In certain cases where samples contain multiple objects, the model may exhibit a phenomenon known as concept bleeding. So this is a big thing. This is a really, really big issue. So if I say a grand piano with a white bench, I didn't say anything about the background. Give me a cool looking background. However, notice the background is white. And the reason it's white is because it kind of had this bleeding where I said white bench and it's like, oh, okay, white bench, I'll produce a white background as well. And that's one of the biggest issues with diffusion. So they make a claim about this. They say, The root cause of this may lie in the used pre-trained text encoders. Firstly, they are trained to compress all information into a single token, so they may fail at binding only the right attributes and objects. So they may negate this issue by explicitly encoding word relationships into the encoding. Secondly, the contrastive loss may also contribute to this, since negative examples with a different binding are needed within the same batch. So the contrastive loss may be causing issues because you have the positive and negative examples. Maybe that kind of conflicts in the encoder. But also, since you have this pre-trained objective, it may not extract the right information from the text for the diffusion model to use. So that's one idea that they have, and it'll be interesting to see if this issue can be fixed, because this is the biggest issue in diffusion, or one of the biggest issues with diffusion. And those are the failure cases they mention. So there we go. Stable Diffusion XL.